So, quick review from yesterday, okay? Projectile motion has two dimensions. A vertical dimension, which undergoes what kind of motion? What is the object doing vertically? It's accelerating because of gravity, okay? And a horizontal dimension where it is traveling at a constant velocity because we're working in the perfect physical world where there are no, hindrances like air resistance and stuff like that, okay? So we know that horizontally it's going to travel at a constant velocity. We know that vertically it's going to accelerate. So what we have to do is sort out our vertical givens and our horizontal givens. Okay? Horizontally, I know that the car travels 165 meters before, well, crashing into the Grand Canyon, Florida. Okay? But that's all I know horizontally right now. Don't know anything else. Vertically speaking, I know that the cliff is 200 meters tall, which means the vertical displacement of the car will be 200 meters down. Okay? I know one other piece of information, actually I know two other pieces of information vertically. One of them is the acceleration, because it's gravity. Okay? And what's the other piece of information? Initial velocity, what is it? It's 0, because they drove horizontally off the cliff. They were not moving vertically at time 0. All right, so that's the information I have. What they're wanting is, what was the horizontal velocity of the car? What do I need in order to get that? Time, yeah. And time is the one thing that both the vertical and horizontal dimensions share, because once the car crashes into the ground, it isn't doing either one of those things anymore. Okay? So, can I find the time with this information? Pretty sure I have a formula that has time as well as the other variables in it. The one we've used on every single problem so far. Okay? Since VI is 0, I can get rid of that, and I'm solving for t. So d divided by 1/2 of a square rooted should give me t. So t will equal the square root of 200 divided by 1/2 times 9.81. .39 seconds. That is a long time to look at the canyon floor rushing towards you. Okay? It gives you some contemplation time. I don't know what you would contemplate because there's nothing you can do about it at that point, but okay, it's a long time to think. 6.39 seconds. Okay, so time goes over here. That's the one thing they share. Can I find V now? I can, because I have to understand that because it's traveling at a constant velocity, this formula can be used with the horizontal information. Right? And all I have to do is plug in my numbers. 165 divided by 6.39 seconds, obviously with all the decimals in place. So 165 divided by the answer there. All right, they were driving at 26 meters. Actually, we have three significant digits. 25.8 meters per second. When they went off the cliff. Okay? If you look at the two examples we did yesterday and this example, those are the only three ways I can ask a horizontally projected projectile question. Okay? There aren't any other manipulations of that I can give you. Did every single one of them involve using the same vertical formula and the same horizontal formula? Okay? That's what makes the horizontal ones easier. Okay? The ones that are projected at an angle, they're a little trickier because there's a whole bunch of different things I can ask you for and a whole bunch of different ways I can manipulate those. And they involve vector components. All right, so on that note, actually let's have you try this one. This is another example of the horizontal one. Okay, so how high must a cliff be so that a person who runs off the cliff, these are violent questions, who runs off the cliff at 8 meters per second, oh, it's water, okay, so they're going to live, okay, would hit the water 15 meters from the base of the cliff. So this is like a cliff diving question, kind of. Okay. So they're running off the cliff at 8 meters per second, and they would hit the water 15 meters from the base of the cliff. All right, that's what we know. Give you a few minutes on that one. So for this one, okay, we want to break it up into our vertical and horizontal dimensions. Okay. Vertically speaking, the question appears to give us nothing, but actually gives us two pieces of information. What are they?
Initial velocity and acceleration.
Initial velocity and acceleration. Okay, they ran horizontally off the cliff, so they weren't moving vertically at time 0, so initial vertical is 0. Okay, and the acceleration is 9.81 meters per second squared down. That's all I know vertically. Okay, the other two pieces of information they gave me were horizontal pieces of information. Right, and so that's going to be the horizontal velocity, 8 meters per second, and the horizontal displacement, 15 meters. Okay, what can I calculate with those two numbers? Time. Yeah, it's traveling at a constant velocity horizontally, right? So I can go V equals D over T and manipulate for T. So T equals D over V, 15 over 8. All right, that's going to give us 1.875 seconds, which can then be brought over to my vertical information, 1.875 seconds. And now I can do this. D equals VI times T plus 1/2 AT squared. And I'm actually looking for D this time, the height of the cliff. Okay, so this is 0. All I have to do is plug in my numbers. 1/2 times 9.81 times 1.875. So it's not a really tall cliff, not really tall. All right, so it's 17.2 meters. Actually, we only have one significant digit there, so 2 times 10 to the 1 meters. So twice the height of a 10-meter diving platform. I don't know if anyone's jumped off a cliff higher than that, but that'd be scary. Okay? So 2 times 10 to the 1 meters would be the height of the cliff. Okay? You could, but it's not proper scientific notation. Scientific notation should always have a base that is between 1 and 9.9. Yeah, I think in French math they teach something different, if I recall, because I get a lot of scientific notation that's not truly scientific, and it's almost always someone did math in French. So I think the French must do it different. Okay. All right. Questions on that one? Okay. Then. If I project something at an angle, is it going to go further than if I just run horizontally? Definitely, okay? Because it's going to have now, instead of having an initial velocity of 0, it's going to have an initial velocity of something not 0 that's upwards, okay? So now gravity has to slow it down and then start moving it downwards, right? So you're naturally going to move further, okay, if you have something projected at an angle. All right, so let me show you a video here. This one's another so do you suppose you could do the calculations and figure that one out and actually place the pool in the right spot? Absolutely you could. Would you bet your life on it? No. Even if you did put that pool in the right spot, that is not what would happen when you hit the pool. Okay, has anyone ever seen one of those little inflatable kiddie pools like that? Okay, like if you lean on the side of them too hard, they fold down and all the water goes out. Okay, they have like 0 structural integrity and not that much water in them. Okay, if you'd have hit that pool at the speed that guy was going, not only would you have pushed all the water out of the pool, you would have pushed the pool right off of that wooden thing and broke your back if you were lucky. okay? Because you gotta think about the speed that guy would have been moving at when he hits that pool. Now, could I absolutely do those calculations and put that pool in the right spot? Yes, absolutely, that's 100% possible. That is the entire principle behind artillery. Okay, being able to lob something from one point to another, you can absolutely do that. Would you do this? No, I don't think so. Okay, so this one was like one of the early YouTube viral videos when YouTube like first came out. Okay, this got millions of views, which at the time was a big deal. Okay, and so everyone sent it to you know who, the Mythbusters, and they tested it. They did it. Okay, I'm going to show you that now because it's funny. Let me copy this example down. This is the slide. Okay, so they're going to go down the slide and then they're going to go flying off the end. Okay, here's the information we know. Okay, we know that the object is moving at 20 meters per second when it leaves the ramp, or the person. And that the ramp, as they told us, was angled at 30 degrees. Right? We want to calculate how far they would travel horizontally. In other words, where do we need to put the pool? Okay, that's what we're going to calculate. Okay, so there are some similarities between the type of horizontally projected projectile motion we were talking about before and projected at an angle. There are some similarities. It does have two dimensions. Okay, it has a vertical dimension and it has a horizontal dimension. Vertically speaking, the object is going to undergo accelerated motion due to gravity. But now I'm going to make that negative. I didn't make it negative before. Why am I making it negative now?
Because we're going up for part of it?
Right. We're going to change directions in this one. Okay? Initially, we're going to have a vertical velocity that is up. And obviously at the end, we're going to have a vertical velocity that is down. Okay? Horizontally, object is still going to travel at a constant velocity. Okay? So those two things are the same. What's different is now my VI vertical is not 0. Okay? So I need to calculate it. What I have is this 20 meters per second. Notice I didn't write that as a given in either the vertical or the horizontal parts because it isn't either one of them. It's 20 meters per second, 30 degrees above the horizontal. It is not horizontal, nor is it vertical. But it does have a horizontal component and a vertical component. Can I calculate those two things? X and Y. Right? I mean, it's really just a vector with an X and Y component to it. Okay? The X component is going to end up being the horizontal velocity, which we know is going to be constant. The Y component is going to be my initial vertical velocity. Okay, why just initial? What happens to the vertical velocity?
It'll accelerate downwards.
Yeah, it's going to change. There's an acceleration going on vertically because of gravity. Okay, so if I want to calculate VI vertical, okay, it is the opposite side of this triangle, right? And I have the hypotenuse of this triangle. So I'm going to go sine of 30 times 20 meters per second, which is going to give me 10 meters per second up, or positive 10 meters per second. Okay. I can calculate my horizontal velocity by calculating the x component. So that's the adjacent side. Cos of 30 times 20. Whoops. 17.321. Okay, they want, or we're supposed to be calculating this distance here. In other words, where to put the kiddie pool. Is that a vertical or a horizontal number? It's horizontal. It's how far from the ramp I need to put the pool. Okay, that is measured along the horizontal distance. Okay, so I need to calculate the horizontal distance. What am I missing? Time. All right, so I can't get my time from my horizontal information. I only have one piece of horizontal information. Vertically, I've got A and VI. Now, here's something we have to assume. The ramp, which starts here, and the pool, and you can see that in the video, the original video, not the Mythbusters video, that those were the same height, because the pool was just a little ways up the hill, so it was actually level with the end of the ramp. Okay? If the takeoff point and the landing point are level, what is your speed? How does your speed when you hit the other side compare to the speed when you left? How do they compare? They're the same. Think about it. This thing leaves my hand, it's moving at 5 meters per second. As soon as it leaves my hand, gravity is slowing it down, slowing it down, slowing it down. Eventually it gets to its maximum height where its speed is 0. Okay, then it falls exactly the same distance at exactly the same rate of acceleration back to my hand. Well, it has to return to my hand at the same speed it left at. Everything else is the same. Okay? There's no way it could be going faster or slower when it returns to the same height. Okay, everyone follow my logic on that. So if my initial velocity is 10 meters per second up, my final velocity is okay. Now, that's only true if the takeoff point and the landing point are equal heights. Okay, that's not always going to be true. There's one other piece of information. In this situation, what is my vertical displacement? Think about that bottle I threw up in the air. Came back down to my hand. 0. The total vertical displacement in this question is 0. It returned to the same height it departed from. Okay? Therefore, its initial position and final position vertically are the same. Okay? So, we'd also have that piece of information. Okay? We rarely use that, though, if I know this is true, because this is easier. Can I get the time if I have initial, final, and acceleration? We can use our good old sine 10 formula. Okay, VF minus VI over T equals A. I've got the acceleration, I've got the two speeds, I'm just solving for time. Okay, so if I go T equals negative 10 minus 10 over negative 9.81, I should get the amount of time that it's in the air for. Okay, so they're going to be flying through the air for just over 2 seconds. Okay, can I take that number and put it over here? I can. Okay, it's still projectile motion. The time is shared by both dimensions. Okay, well, D equals V times T. Okay, 17.32 times 2.04, and that should tell me exactly where to put the pool. Okay, I put the center of the pool 35.3 meters away. Then I hit the pool. okay with that idea? Okay? That is the basis for all projected at an angle projectile questions. Okay? This is the same calculation that stunt coordinators use in movies to determine angles and speeds that cars need to be jumped at if they want to practically film a car jumping something, which they don't do as much anymore, because it's easier to CG it and make it look stupid, you know, like Fast and Furious. At some point, we're gonna watch the video of the 10 times the Fast and the Furious ignored reality. That list could be a lot longer, but it's just the top 10 times that they ignored reality. Okay? Now, one other thing. This is the scarier part. Could I calculate the maximum height above the ground that this person would reach? Okay? I could. Where is it going to occur? Like in this arc that they're going to follow, where would the maximum height occur? Right in the middle, right here. Okay, so if that's where the maximum height is going to occur, okay, how fast is the object going vertically at that point? 0. That's where it turns around. Remember when I threw the bottle up in the air, its maximum height is where it stops for a second before it actually starts to drop back down. So if it ever asks you to calculate the maximum height, you know that at the maximum height, the velocity is 0. In terms of time, when does that occur? If that flight took 2.04 seconds, when does the maximum height occur? 1.02, halfway. Okay, so there's all these other pieces of information you can get if you're dealing with the maximum height. Okay, so this is what I would do. The initial velocity would still be the positive 10 meters per second. Okay, that's not changing. The final velocity is going to be 0 meters per second, and the acceleration is going to be negative 9.81 meters per second squared. And I'm trying to find the height, which would be the vertical displacement at that point. Do I have a formula that has VI, VF, A, and D in it? Pretty sure I do. Pretty sure it looks like this. Okay. So I could solve for D with that formula. Right? I would just have to subtract VI over to the other side. Divide both sides by 2A. Okay? We had to do that back in the acceleration part of the unit. So 0 squared minus 10 squared divided by 2 times negative 9.81. So we're going to have 100 divided by 19.62. Okay, so that person is going to reach a maximum height of 5.1 meters. That's like most of the way up the gym. Okay, to give you an idea. Okay, a basketball hoop is 3 meters tall. So this would be at least another meter above the backboard. Okay. I wouldn't want to fall from that far up. Okay, that'd be scary. Those are the kinds of things you're going to be asked, okay, for a projected at an angle projectile question. All right? Now. No, that's a horizontal one. Okay. Let's look at some good movie physics. Okay. Not too many movies now get shot with practical effects. It's a lot more reliance on computer generation. Okay, but back in the day, and I mean like way back in the day, when you wanted to have a shot of a car jumping something, you had to film a car jumping something. Okay, the best show to ever do that is The Dukes of Hazzard. Okay, I don't know if any of you have seen that because it's not on TV anymore because there's a Confederate flag on the top of the General Lee, which is understandably not cool. Okay, so the show is no longer on TV, okay, because of that. Okay, even though the show itself is actually quite wholesome, obviously we can't have a symbol like that being on television. Okay, so they would jump these cars. So the General Lee was a '69 Dodge Charger. It was a beautiful car, bright orange. Okay, and they jumped several hundred of these cars over the course of the 7 seasons that the show ran. Okay? By the time the show had run its course, they were having trouble finding Chargers to jump. So they were actually filming Challengers from different angles because they looked similar from different angles to do the jumps because they had written off so many of these cars. In fact, they reused some of the jump cars a second time. You can actually catch it in some of the shots. You can see that there's already damage on the car, and they're just jumping an already damaged vehicle, okay, because they were just, well, we don't have a car today, so we'll just reuse that one from 2 weeks ago. Okay? Is it fairly straight? Can we make it go in a straight line? Okay? But back in that time, all those cars had a stunt driver. Okay? There was no remote control on those cars. There was actually a driver in those cars for the jump. Okay? So it was a little more realistic, we'll say. So let's say we know the following information about this jump. Okay, so the General Lee, which is that orange car, okay, is jumping the riverbed. The speed of the General Lee is 32 meters per second when it leaves the ramp, because of that big pile of dirt that was there. Okay, and it's angled at 20 degrees. What is the distance across the river, and how high did the General Lee jump in making this jump? Okay, so what we realistically know is this. That's it. Okay, we know that the General Lee was moving at 32 meters per second when it left a 20-degree ramp. Now, what kind of a path did the General Lee follow as it flew over the river? If I was drawing a shape of its path, what would it look like? A curve, yeah, an arc. Okay, so we know that it's really going to do that. Okay, that's the flight path of the car. The question wants to know what's the horizontal distance and what's the maximum height or vertical distance? And it only gives me 32 meters per second at 20 degrees. Does that seem very fair? Doesn't seem like very much information, except there's other things that we can get from that. Okay? As in all projectile motion projected at an angle, this has an x component that represents the horizontal velocity and a vertical component or y component that represents the initial vertical velocity. So as long as I get that projected velocity, I can calculate the other two things. Sorry, I said 20 degrees, not 30 degrees. I wrote 30 there, but it's actually 20. Okay, how would I calculate the horizontal velocity if that's what I know? How would I calculate x? in that triangle, x is which side? Adjacent, opposite, or hypotenuse? It's adjacent. Do I know the hypotenuse? I do, it's 32. Okay, so if I want to calculate that horizontal, I'm just going to go cos of 20 degrees times 32 meters per second. Okay, so horizontally, the car is going to travel at 30.07 meters per second. And that is not going to change. It will travel at that constant horizontal velocity the entire time it's flying through the air. Okay. Can I calculate VI vertical? If it's the y component, I certainly can. I just go sine of 20 times 32. Okay, so 10.94. And that's going to be up. Okay. Now, we do have to make an assumption here, and it's safe to make this assumption because they haven't told us otherwise. The takeoff point and the landing point are level. Okay? If they're level, the overall vertical displacement front to back is 0. And that means VI and VF are equal, but opposite. One's up and one's down. Okay? If you were to watch only the vertical part of this, you would see a car go up and down. If all you could see was the vertical part of this action, you would see the car go up and back down to the same height. Okay? Because that's all that's really happening vertically. Okay? So VF is going to be negative 10.94 meters per second, and the acceleration is going to be negative 9.81 meters per second squared. Okay, the question wants to know the horizontal displacement. Can I get that? What do I need? I need time. You always need time. I don't mean that, I mean you always need time. There's never enough time in a day, but you also need time for this kind of question. Okay, and I can get it with VI, VF, and A. Right? I can say that T Alright, so we're going to have positive 10.9, or sorry, negative 10.94 minus 10.94 divided by negative 9.81. Okay, so generally is going to be, whoop, I said 10.64, I meant 10.94. Sorry, 2.23 seconds. Okay, can that number go here? Okay, right? Time is the one thing that both horizontal and vertical share. Okay, D equals V times T. Okay, so we would have our 30.07 times 2.23 seconds. Okay, that river is 67 meters across. Is that a long way to fly in the air in a car? Any distance is a long way to fly in the air in a car, but 67 meters is a really long way. It is 2/3 of one of the straight sides of the running track. Okay, so like that front straight there, it's 2/3 of that. So like they jumped from that building back there and landed more than halfway. Okay, long way across.
Which formula did you manipulate?
I manipulated A equals VF minus VI over T.
Oh.
Solve for T, and then V equals D over T after that. Okay? All right, everyone following me so far? Am I using everything but graphing that I've learned in this unit? I'm using vector components. I'm using v equals d over t. I'm using acceleration formulas. Okay? And we've only gone over really one kind of projected at an angle problem. The mega whoosh and this are exactly the same question. Okay? They're just different context, but the same type of question. Nope, before you back up, we still haven't calculated the maximum height of the general lead. Okay? That happens here. What do I need to remember about VF here? It's 0. Okay? Or that it's how much of the time? Half. Okay? So if I wanted to, I could use a different formula than the one I'm going to use, but use half the time instead. Okay? So I'm going to say that D equals VF squared minus VI squared over 2A. So that's the one that's VF squared equals VI squared plus 2AD. Okay, just manipulate it. So 0 squared minus 10.94 squared divided by 2 times negative 9.81. Okay, 6.1 meters. That's more than twice the height of a basketball net. I would not want to come crashing down from that height. Okay. All right, so we'll be looking at some more examples of this tomorrow with more bad movie physics. But first we'll have a quiz. And that quiz will have one horizontally projected projectile question. Okay. Reminder, your map activities, guys, are coming up due tomorrow. So make sure you talk to your group and get that done. Okay?